Initialize it. All right, here we go. We're good.
Hello.
All right, let's see. Come on. What the heck? All right, today we're doing notes. And for those of you who are listening, we're not in chapter 2, we're in chapter 4, okay? This might say chapter 2, but this is from my AP chemistry book. But the notes are the same, and it's not like a really difficult lesson where you're going to need to have some kind of college experience in order to understand this, okay? This chapter we're going to focus on the atom and what makes up the atom, the inner workings of the atom, the electrons, the protons, the neutrons, isotopes, things like that. All right, let's get started. Let's close this little box. All right, we'll start with Dalton's atomic theory. This was in 1808, and he has 3 points. I will paraphrase these, so don't feel like you have to write this entire thing down. I would paraphrase. Basically, his first point he came up with the idea of elements and atoms. And he determined that atoms were the smallest entity that you could possibly get to. In other words, you can't get any smaller than an atom. That all matter is made up of atoms and you just can't get any smaller. We do know now that that's not true, but he was pretty close at the time. You got to remember, he couldn't even see an atom, so that's impressive that he was even able to come up with this idea that elements are composed of these small particles called atoms. But we now know that there's even smaller particles, such as protons, electrons, neutrons, and even smaller than that, there's things like neutrinos and positrons and all these other particles in the atom that are much smaller than the atom itself. All right, the second point, let's paraphrase that. The second point, he came up with the idea of compounds, and this basically, the definition, this one where it says the relative number of atoms of each element in a given compound is always the same, that was a vocabulary word from your last chapter, chapter 3. That's the law of multiple proportions. And basically that says that if you have different ratios of atoms in a compound, then they must be different compounds. And the last one, point 3, you can summarize that entire point up by just writing the law of conservation of mass. And that states that mass cannot be created nor destroyed. Okay? All right. I'm going to shut that door. You're loud. All right, door's shut. Let's continue. I need a wireless mic here. All right, next page. Here's the law of multiple proportions, and this is just there's not a whole lot you need to copy down here or anything, but just kind of look along here. If you had a compound carbon monoxide, it is always going to be composed of a 1-to-1 ratio. So 1-to-1 ratio on carbon monoxide. And if you had carbon dioxide, it's always going to be at a 2-to-1 ratio. And if it's not at those ratios, then guess what? It's not that compound anymore. It's a different compound. So that's what his law of multiple proportions stated, that you always have a certain ratio of one element to another, and if it's different, then it's a different compound. Is there a pointer in PowerPoint that I can grab so I can highlight things for the people who are... yeah, I think the marker's working. You're genius, Cole. Thank you. Okay. What's that? All right. Law of multiple proportions, like I said. Okay. All right, next, Dalton's atomic theory. This is the third one, and this is the law of conservation of mass. And that, if you look on the left there, we've got, I don't know how many of those are. I think that's 16. 16 red balls, red atoms, and then we have 8 of the green, and that would make 8 of the X2Y. It's the exact same number on the left and the exact same number on the right, thus the law of conservation of mass. So there it is, law of conservation of mass at work. And you can just total up 16 x's. Over here we have 16 x's as well. If we take this 8 and multiply it by the 2, that's 16 x's. All right, next we're going to look at a series of 3 famous experiments. And for your notes, I would advise you to, there's going to be a couple video segments and a whole bunch of pictures. And so what I would divvy up your notes into, maybe write as a title, famous experiments, and then have space for 3 famous experiments. What I'm going to test on for the famous experiments is give each experiment a name. All right, we'll discuss the name of them. The first one we're going to call the cathode ray tube experiment. Name the scientist who did that experiment, and what was discovered as a result of this experiment. So that's what I'm testing on in these experiments. So the name of the experiment, who did the experiment, and what was discovered as a result of the experiment. The first one, we'll call it the cathode ray tube experiment, and this was done by J.J. Thomson. And from his famous experiment, he measured the mass to charge ratio of an electron. And he won the Nobel Prize in physics for this. Let me show you what he did. I got a little video of it. Start her up here.
Did you become famous after this?
Yep. Anybody who gets the Nobel Prize, they still give it out every year. There's there's a number of Nobel Prizes given out every year for physics and chemistry and biology. So they were started from Alfred Nobel. He wanted to be known for something more than he was known for as the merchant of death, because he invented dynamite and gunpowder. He wanted to be known for something better than that, so he wanted to be known for these Nobel Prizes. So he came up with these prizes, and they're still given out today. I've deleted my link. All right, I'm going to get it back to it. Oh, this is hard working backwards like this.
We have broken the sound barrier. But how did it get past the space? But where is that music concealed? Okay, this is the cathode ray tube. One essential vacuum chamber. There are no gases inside this glass tube. The only thing we have are 2 electrodes, one called the cathode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it?
Any idea what that beam is? Those are electrons. Okay? So he was able to see electrons, and a very simple device here. It's basically a vacuumed out glass tube, and a vacuum means that there's nothing inside there, no gas, nothing. There's actually a little bit of gas because it's very hard to get a perfect vacuum, but for the most part it's a vacuum. And then he hooked it up to a power supply, and as a result, when you hook it up to a power supply, electrons travel through the chamber, and one side has a positive and one side has a negative, and the electrons travel from one side to the other, and the fluorescent screen allows you to see the electrons. So when you plug something into the wall to make it work, what you're doing is harnessing the power of the electrons to make your appliance work, your vacuum cleaner turn on, your phone charge, whatever. Okay? So what you're looking at there is a beam of trillions and trillions and trillions of electrons traveling from one side to the other.
We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. I'm going to apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving. It's being repelled, isn't it, by the magnet? When we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now, at the time, that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound? Because hydrogen is the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron.
All right. Nice. He said one thing wrong in that video. He said that J.J. Thomson then discovered that the electron is has a mass 2,000 times smaller. He didn't actually discover that. He just discovered the charge to mass ratio. You're going to see that in another famous experiment. In the other famous experiment, the mass is revealed, and that's coming up. All right. Next experiment is Milikan's oil drop experiment. I have some slides that go through that same experiment that he did, but I think seeing a video is much more impressive than seeing the electron beams get deflected. So I'll just kind of click through those really fast. But here's the same thing. He was able to deflect the electron beam, thus now knowing it has a charge and he was able to come up with this, what's called charge to mass ratio. Now, second experiment after Thomson. Thomson's experiment occurred first. Another person, Milikan's famous, we'll call it the oil drop experiment. And what was discovered from this experiment is Milikan was able to figure out the actual mass of an electron. And here's what he did. He took oil and he put it in this thing called an atomizer. It's the same thing as like a perfume bottle. You squeeze on the bulb at the end, and little droplets of oil sprayed into this contraption. And as oil droplets sprayed into the contraption, some of them gain static electricity. And as they gain static electricity, that means there's now electrons on the oil droplets. So due to gravity, some of these oil droplets would then fall, and there's a little tiny hole right there. There's a little hole in the plate, and so, once in a while, an oil droplet would fall right through the plate, and it would start to fall due to gravity, of course. But then what he was able to do is he was able to focus in through his viewing microscope that little oil droplet that fell through. He was able to find it. And see these plates? There's a plate here, and there's a plate here. On those plates, he then put another electrical charge. What he was able to do, he was able to adjust the electrical charge until this oil droplet stopped falling and actually just stood there and floated in space. And as it floated in space, he then measured the charge that he put on these plates. And based on the charge that he put on these plates when that oil droplet stopped falling, from that, he was able to get rid of the charge portion of Thomson's mass-to-charge ratio and able to then just figure out the mass of an electron. So he measured the mass of an electron. He also won a Nobel Prize for doing this. And he was able to figure out by measuring what charge you put on the plates at a value of negative 1.60 times 10 to the negative 19 coulombs. You don't have to memorize any of these numbers. He took Thomson's measurement of this, and from the two measurements, he was able to figure out that the mass of an electron is 9.10 times 10 to the 28 grams. Negative 28 grams. My circle got in the way there. Let's see if I can erase it. Good. Okay. So very, 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 very tiny. I don't need you to memorize the number of the mass of an electron. I just need you to know that it is incredibly tiny compared to that of a proton or a neutron. It's about 2,000 times smaller in mass than a proton or a neutron. Okay? All right, next experiment. Rutherford. Third experiment, you need to only know three famous experiments in this chapter. It's called Rutherford's. We'll call it the gold foil experiment, done by Ernest Rutherford. In his experiment, he took a radioactive sample, put it in this lead box right here, and that radioactive sample sent out alpha particles, and he shot them. He shot them at this gold foil. Why did he use gold foil? I don't know. It really didn't matter what kind of foil he used, but he used gold foil. And he shot these radioactive particles at this gold foil, and what he noticed was that most of the radioactive particles went right through it, went right through the gold foil. However, to his astonishment, once in a while, he was able to detect that a particle actually hit something and bounced back. So it hit something in the gold foil and bounced back, and this really shocked him because he thought these alpha particles were so tiny they should be able to pass right through the gold foil without it ever stopping, and it just passed right through. So what did it hit? It must have hit something really dense and very positive. And the reason why he knew it was positive, because he knew that his radioactive sample was also positively charged. So his radioactive sample had a positive charge to it. So it must have hit something really, really densely positive, and it repelled it straight backwards. There's a famous line from him, and he said, "It was as if I shot a cannonball at a piece of tissue paper, and it bounced back." So he was very, very shocked at what he observed. Okay, so based on this, what did he discover? What's in that atom that it bounced back from? These things. What are those? Those are the nucleus, right? So he hit the nucleus. Before this point, there was no knowledge that a nucleus was in an atom. So he discovered not only the nucleus, but he discovered that the nucleus was this extremely dense region of positive charge. Okay? So this is, in summary, what he found. Atom's positive charge is concentrated in the nucleus, and that the protons has an opposite charge of electrons, and that the mass of a proton is about 2,000 times the mass of an electron, 1,840 to be precise. The first point is what you need to know in terms of what was discovered from this experiment. The other 2 points just came along with the experiment. Okay? All right, let's look at what was discovered. These are statistics that you don't need to memorize, but are just interesting, just to give you a relative appreciation of the atom. So if we took an atom and we made it the size of a giant football stadium, the nucleus would only be as big as a marble at the 50-yard line, and the rest of that would be electrons just buzzing around. But here's our nucleus, tiny little dot right in the center. The rest of it is these electrons buzzing around in what's called the electron cloud. We're not going to learn Chadwick's experiment. That was the discovery of the neutron, but we're going to skip that one. All right, a couple of things from this slide right here. Once again, you do not need to memorize the numbers, the specific mass numbers of masses of electrons, protons, and neutrons, but what I do need you to know is that an electron's charge is thought to be -1 relative to a proton, of a proton being +1, and a neutron having, just, you can hear it in the name of it, neutral charge, 0 charge. So neutron has no charge, but electrons and protons have opposite charge, a positive and a negative. Check out their masses over here. These are so close that many times we'll say that they have the same mass. So 1.672, 1.674, they're so close that most of the time you'll hear people say that the mass of a proton and the mass of a neutron are the same. And they are virtually the same, but they're slightly different. Electron has much tinier mass, -28 versus a -24, much smaller mass. All right. Lastly, let's learn about isotopes, and then we're done. Okay. Get used to this notation right here. This is a notation that we're going to use all year long, okay? So get used to that notation. we're going to use that notation in order to figure out the mass of an isotope. Okay, what are isotopes? I have a definition right there. Isotopes are atoms of the same element with different numbers of, the key word is neutrons. So atoms of different atoms with different numbers of neutrons. Atoms of the same element with different numbers of neutrons. Let me say that right. In this notation, the X represents our element symbol, such as off the periodic table. Calcium, Ca. Potassium, K. Oxygen, O. Germanium, Ge. Things like that. The top number. The top number represents the mass of the isotope. And the bottom number represents the atomic number. The atomic number is equal to the number of protons in the nucleus, just like that says right up here. All right, let me give you a couple examples. 3 examples of that. Hydrogen. Hydrogen isn't all the same. There's actually 3 different versions of hydrogen. There's the first isotope, we just call it hydrogen 1. The second hydrogen, we can call it hydrogen 2. The third hydrogen, we can call it hydrogen 3. The second and third kind of have some fancy names to them. The second one's called deuterium, and the third one's called tritium. So those are 3 different isotopes for hydrogen, and they each have slightly different uses for them. But don't get me wrong, they're all still hydrogen. Notice what they all have in common. They all have the bottom number in common. The bottom number, the atomic number, that is, once again, the number of protons. Where do we get that number from? Just look at the periodic table. That's the number on the periodic table. It's element number 1. And so that is the number of protons in that sample of hydrogen. And it's always going to be the same. 1, 1, 1. If it wasn't 1, what do you have? Anybody? If that number was 2, it would be a different element. Yes, thank you. Okay? If you had a different number there, it would no longer be hydrogen. It would be a different element. So, erase that. Let's do this. How many protons, how many electrons, and how many neutrons are in each of those 3 isotopes? First of all, the protons and electrons, those are so easy to calculate because protons are always going to be the same as the atomic number, and the atomic number will be the bottom number. So the protons will be 1. The proton for this one will be 1. The protons for this one would be 1. How about the electrons? They're also going to be 1 and 1 and 1. The electrons and protons will be the same for all atoms. When are they different? They're different when you have ions. Ions are charged atoms. But right now we're just talking about neutral atoms. The protons and electrons are exactly the same in neutral atoms. Since these are isotopes, the one thing that will vary is always going to be the neutrons. And how do we figure out how many neutrons we have? Simply use this formula. The mass is going to be equal to the protons plus the neutrons added together. The mass number is also equal to the top number on all of these isotopes. So if we plug those top numbers into the formula, 1 is equal to the number of protons, so we'll do the first one, 1 plus, what does the neutrons have to be? 0. Okay? How about in the next one? What does the neutrons have to be? 1. And in the next one, the neutrons would have to be 2. Okay? That's how it works. Just simply subtract. Just take the top number minus the bottom number, and that's going to be the neutrons every single time. Those protons and neutrons, once again, are in the nucleus. The electrons are buzzing around on the outside. Two different isotopes. We'll skip those ones. Let's go to here. Tritium. Tritium, I just wanted to give you an example from maybe something that you saw, like in the movies. Spider-Man. Spider-Man, Doc Octopus. Okay? What was he trying to do? Anybody who saw the movie? He was trying to do stable nuclear fission. Nuclear fission is occurring on the, fusion, not fission, fusion. It's a big difference. So he was trying to do stable nuclear fusion. That occurs on the sun. Sun is constantly taking hydrogen and hydrogen, combining them together to make helium. We can do that here on Earth. We can do it. That's called a nuclear bomb. Okay? And it produces a tremendous amount of energy. What Dr. Octopus in the movie was trying to do was do this stably and produce a tremendous amount of energy in order to be a source of energy for society. But that's really dangerous because it's not controllable. That's why we use it for a nuclear bomb, because who cares if we can control it? We don't want to control it. That's the whole point. We want it to blow up and cause destruction. But if you could control that reaction, you could produce a tremendous amount of energy for good. And that's what he was trying to do. In order to do this, he needed to find tritium. Tritium does not look like a little gold ball. Sorry. It looks like hydrogen gas, but it's just a very, very rare type of hydrogen gas. Maybe he has tritium inside that gold ball, but I'm uncertain. So it was kind of a little bit far-fetched in the movies that he was able to gather together so much tritium when it's extremely rare, and about the only place you're going to find it here on Earth is nowhere. You're going to find it on the sun. So you can find a lot of it on the sun, but you're not going to find it really here on Earth. So that is another fictional part of the movie as well. All right, there's what our three isotopes would look like. That's what their nucleuses would look like. The first one with just a single proton, no neutrons. There's one of each. And there's two neutrons and one proton. Okay? All right, let's see what you learned. I got to erase the answers. Whoops. Okay, let's see what you learned here. Do you understand isotopes? How many protons, neutrons, and electrons are in carbon-14? You've probably heard of carbon-14. What do you use carbon-14 for? Biology. Cole, you were in my biology class.
I'm trying to think. Is it radioactive?
Radioactive dating. Correct. Okay? Radioactive dating. So you use carbon-14 to date things, to figure out how old they are. All right, so carbon-14, the protons, what would the protons be? 6. Oh, what the heck? Let's go back. Back, back, back. I'll just write them myself, I guess. Protons are 6. They're the bottom number, right? The electrons are 6. That's the bottom number. And the neutrons are 8. 14 minus 6. Okay, 8. So That's all there is to it in order to figure these out. Very, very simple. Hi, welcome back. Is there more of you? You just came back before the rest? Okay. One more example, and then we're done. Another version of carbon, carbon 11. How many protons, electrons, and neutrons? 6 and 6, right? It's the same exact amount. And then the neutrons would be what? 5. 11 minus 6 to get 5. Carbon 14 is used for radioactive dating. So that's how you tell how old a mastodon is, or some old bone. They dig up some skeleton and they figure out how old that skeleton was. Okay? That's what you use carbon 14 dating for. I was actually watching a show. No, it was actually Agents of S.H.I.E.L.D. I was watching it with my daughter on TV, and they were talking about this sand, and they were saying how old the sample was, and they said it predated Earth's age, which the Earth is how old? I think it's 4.1 billion years. They were saying that this sand that they found was 5 billion years old, which is impossible. And they recognized that it was impossible, but they said they figured it out by carbon dating. Guess what? There's no carbon in sand. So you can't use carbon dating to figure that out. Also, carbon dating only works for about 50,000 years. And then there's no more carbon left to do carbon dating. So they had two things wrong in the story of that.
Pardon the interruption, but please allow any junior that took the PSAT into the 6-hour class at this time.
All right, we are done.